Hello everyone, you are currently in the chapter Complex Calculations on AC Circuits. In the following video, we want to work on a problem where you have to determine the impedance of an electric circuit that consists of a resistor, a capacitor, an inductor, and an AC voltage source. In addition to that, we will also calculate the electric current that flows through the whole circuit. And in all calculations, we will be using complex numbers. And here's the equation that's the centerpiece of this exercise. It has a resistor and a parallel subcircuit that is made of an inductor and a capacitor. The voltage source provides voltage that's expressed by this cosine function. And the parameters for each component are provided here. As I said before, we will be using complex numbers to compute the impedance of the circuit as well as the parallel subcircuit, because if you have a capacitor or an inductor or both, you have a phase shift that occurs when you apply a voltage and then you measure the current. And to take the phase shift into account, it is convenient to use complex numbers. And I'm gonna give you the information right now that if you want to add impedances or reactances of each component, you better use this rectangular form of complex numbers. However, if you want to multiply or divide complex numbers because you want to find the current from a given impedance and voltage, you want to use this exponential form. Later on, we will show you how to convert from the rectangular form into the exponential form. For now, let's get started with calculating the impedance of the parallel subcircuit. The equation for the impedance of that subcircuit will be 1 over underlined X sub LC. The LC reflects the fact that the subcircuit consists of a capacitor and an inductor. And the underlining of the X means that we are working with complex numbers. I will not be mentioning the underline verbally, just for convenience. But I will write it down, of course. Because the subcircuit is parallel, we're going to use the same approach as you use for a parallel circuit or subcircuit if you don't use inductance, capacitors or inductors. It's going to be 1 over XL, the reactance of the inductor, plus 1 over XC. And if you have followed the course, you know that the equation for XL that uses complex numbers is J times omega times L plus 1 over the inverse of J omega C. And J refers to the imaginary axis on the coordinate system. We have a real axis on as the x-axis and an imaginary axis on the y-axis. And because we are taking the inverse 2 times, we end up with 1 over J omega L plus J omega C. We're gonna simplify it further. 1 over J omega L is equal to minus J times 1 over omega L plus j omega c. And that is equal to j times minus 1 divided by omega L plus omega c. That's the complex form of the impedance of the parallel subcircuit. And now let's plug in the values that are provided. Sorry, I forgot to underline this x. It's gonna be j times, okay, we have a lot of numbers to plug in here, minus, I'm gonna start with the denominator, 10 to the minus 7th power radians per second, or just 1 over second. That's for the angular velocity, times 2 times 10 to the minus 6th power Henry, the unit for inductance. 2 times 10 to the minus 6th power is equivalent to 2 microhenry. We're gonna put the divider. Plus 10 to the 7th power, 1 over second, times the capacitance, which is 10 microfarad, and 10 microfarad is equal to 10 to the minus 8th power farad. And that whole thing is equal to j 0.05. So we have a value that extends into the imaginary axis only. We have no value whatsoever extending into the real axis. Okay, that's not the impedance of the subcircuit yet, because that's just 1 over the impedance. We have to take the inverse to find the actual impedance expressed as a complex number. That's equal to 1 over j times, I'm not going to use the times symbol, 0.05. And that's equal to, similarly to what we did above, 1 divided by j is minus j, 1 over 0.05, and that's equal to minus j20. So the impedance of the parallel subcircuit extends into the negative region of the imaginary axis. As I said, that's just the impedance of the subcircuit. In order to compute the impedance of the whole circuit, we need to add the resistance to that impedance. Let's do that. It's going to be quite quick. X and the impedance of the whole circuit will be labeled as X underline RLC. XR, the resistance, plus XLC. And here you can just add the numbers. XR, where the resistance is 50 ohms. I will leave out the units for convenience because we're dealing with complex numbers. Minus J20. What does this expression mean? It means that if you draw the impedance in the form of a phasor on this coordinate system, the phasor will extend 20 units downwards on the y-axis or the imaginary axis, and 50 units to the right. Let me draw that phasor for reference. 50 units to the right and 20 units down. The phasor looks a little small in this case, so I apologize for that. And we also have the phase angle, which we will call theta. We'll just squeeze it in between the numbers. And the phase angle theta, which we will compute just in a few seconds. Actually, let's compute the angle and also the absolute value of the impedance. I'm saying absolute value because what we've computed here, that's not the actual value of the impedance, that's just a complex expression to calculate the absolute value of the impedance, and hereby the impedance itself. You need to apply Pythagoras' theorem. So I'm going to label the absolute value of the impedance by using the two bars to the left and to the right. And that's equal to the square root of the real part squared. So square root of 50 squared plus 20 squared. Well, actually it should be plus minus 20 squared, but if you square a negative number, you're going to have a positive number anyway. So we will be using a positive number. The square root of 50 squared plus 20 squared is equal to 53.85. And that's the absolute value of the impedance of the whole circuit. It can also be interpreted as the length of the phasor on this diagram. And the phase angle theta, let's also compute that quickly. As you can see from the set of equations for complex numbers, the phase angle theta in this case is equal to the inverse tangent of the imaginary number, the imaginary part of the complex number divided by the real part, b over a. In our case, b is 20. That's what follows after the j. It's actually minus 20 divided by 50. It's the real part. And the phase shift angle is therefore minus 21.8 degrees. What does the phase shift angle mean? If the value is negative, as in our example, minus 21.8 degrees, it tells us that the current leads the voltage by the respective angle. If you were to draw a sine or a cosine curve representing the voltage and the current of the whole circuit, you would see the current function being shifted ahead by 21.8 degrees. You could also say that the voltage lags behind the current by that angle. On the other hand, if the phase shift angle was positive, let's say plus 21.8 degrees, you would have a situation where the voltage leads the current by that angle, or the current would be lagging behind the voltage. Okay, in the next step, we're gonna calculate the current that flows through the whole circuit. And for that, we will be using complex numbers, and we will convert from the rectangular form into the exponential form to perform a division. The conversion from the rectangular form into the exponential form of a complex number is actually quite simple to carry out. You have this equation, and if you have your complex number expressed as a plus jb, the exponential form is going to be the absolute value of z times e to the power of j times the phase shift angle. In our case, x underlined RLC is equal to z, the absolute value, which is 53.85, times e to the power of j times minus 21.8 degrees. And why do we need the conversion into the exponential form? Because now we're going to compute the current flowing through the circuit. And to compute the current, you need to divide the voltage by the impedance of the whole circuit. So I'm going to write down I underlined is equal to the voltage. And again, all of the variables will be provided as a complex expression divided by the impedance. And the voltage is provided as a form of cosine function, but we can easily convert it into the exponential form of the complex number as well, because the absolute value is already given. That's 120 volts. So 120 times E, and the phase shift angle is, or the angle is omega times t minus 30 degrees. So we're gonna put that into the power j times omega t minus 30 degrees. And that whole thing is equal to 120 times e to the power of j times omega times t times e to the power of j times minus 30 degrees. And we need this exponential form because we're going to perform a division. So 120 times e to the power of j omega t, and one more time, to the power of j times minus 30 degrees, divided by 53.85 times e to the power of j times minus 21.8 degrees. And if you carry out this division, you're gonna get 2.28 amps, just to let you know that the unit is amps, but I'm not gonna write down the unit because it's a complex number, times e to the power of jwt times e to the power of j, and then minus 30 degrees plus 21.8 degrees, plus, because minus a negative number means that we add a number, and that gives us minus 8.2 degrees. And this whole thing, that's the function of the current that flows through the whole circuit. And if you want to convert from the exponential form into the cosine form, we can do that right away. I is equal to 2 times 2, 2.28 amp times cosine omega t minus 8.2 degrees. Okay, so that's the function of the current if you have the voltage function as stated here. Well, we hope that you liked this video and that it was helpful to you, and we wish you good luck for the rest of your semester. Thank you for watching.